Okay, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, good. So, how's everybody today?
Alhamdulillah, fine.
Alhamdulillah.
Good.
A bit sleepy.
Why a bit sleepy?
That's in the afternoon.
Yeah,
Why?
sebab time for afternoon nap.
Time for afternoon nap.
Although it's 11:30, so well.
You better not be sleepy in my class. Okay. All right. So, okay, let's continue from last time. So let me see. Okay, you can write the attendance. I already pin in the Telegram. It will be the same link every time, except for the password will be different. So the password today will be mango. I was eating mango this morning. So, randomly. Right, so okay. Sekarang ada musim mangga kot. I think it's everywhere. One of my favorite food is mango. And I think it's one of the creation of Allah, which is saya rasa memang amazing lah mango ni. Yeah, and so if I eat mango, it will remind me of Jannah. Saya rasa macam dekat sugar, you know. Since by eating mango.
Tasted.
It depends on mango lah. Mango yang sedap tu kan, yang manis, yang lemak tu. Right, so okay.
You prefer sweet or sour?
Yes, the sweet tu lah yang kita suka kan. Ada orang suka sour. Now I'm trying to look at your question here. So only how many questions? Madam, what is the difference between interstitial and substitutional impurities in slide 21? Slide 21, slide 21.
Page 21.
Okay, so the meaning is there. Which part? Which part you don't understand, Azam?
I can imagine how it is.
Huh? Apa? Tak dengar lah. Masalah saya ada masalah pendengaran dengan awak ni.
Macam mana dia punya ya bentuk dia.
Ha? Betul?
Belum.
Tak faham lah. Apa yang awak tak faham?
Open the slide again.
Which part you don't understand? So what you don't understand?
Both are foreign atoms, but what's made both different?
So both are foreign atoms. So for you to dope something, doping is adding impurities, right? Doping, it means from the pure semiconductor, which is intrinsic, you add doping. Doping, it means is something not from the material you add on, and we call anything that you add on impurities. Okay, it's a kind of impurities. So these impurities, when you can you imagine that you have this lattice, okay, to the lattice of the material. So imagine this is a pure semiconductor, okay. So let's say the blue is the silicon atom, okay. So then so this already pure, very nice, okay. Then you add impurities. So where the atom goes, okay, this is a piece of semiconductor, right? So the atom of the impurities in the dopant need to go somewhere. Yes or no?
Yes.
Okay. So interstitial means, so let's say I dope the silicon with, what do you dope it to become an N-type? Give me a material. dope it to become N-type? Awak kena tahu tau. Tapi tak apa, open book. Exam awak kali ni pun akan open book.
Arsenic?
Saya tak akan tanya soalan dope dengan apa. Saya akan assume awak akan cari lah. There are in the final exam, I will assume things that memang yang ada yang saya tak pernah sebut pun dalam kelas, tapi you can find. Okay. Tapi the concept you understand. So meaning you just need to find like 2 minit benda tu and then use the concept to answer the question. That's how the open book question will be. Maybe we have 3 quizzes. Maybe one of the quiz I'll make it open book so that awak ada persiapan untuk final exam. Sebab saya rasa my mistake last semester was all the quizzes were closed book. So bila final tu dia orang shocked, terkejut, tak pernah buat open, tak pernah ada pengalaman buat open tu, tengok wow soalan macam nak pengsan lah. So I will give you so this time I'll give like a warning by rehearsal satu quiz open book lah insyaAllah. Sebab dia punya style soalan tak sama tau, open book dengan closed book. Closed book yang zaman-zaman dulu tu, sebab tu in a way you need to understand, sebab you want to use past papers pun tak boleh sangat sebab dia tak sama gaya soalan tu kan. Saya takkan tanya soalan oh what you do, benda-benda senang-senang yang boleh google satu saat tu, memang takkan keluar lah soalan macam tu. Dia akan keluar soalan-soalan yang okay, if this situation macam ni, situation ni, saya nak buat macam ni, macam nak buat. So kena berfikir. Dia banyak soalan yang berfikir. Sebab tu saya suruh tanya soalan supaya awak boleh start berfikir from now. So for example, we want to make it N-type. We dope it with the donor atom. So let's dope it with phosphorus atom. So this is a pure silicon. This is a pure silicon. We want to dope it to become N-type, means that we need to put impurities, which is the donor atom now, phosphorus. So let's say the phosphorus blue sini. Atom. It needs to go somewhere. If the atom is here, okay, so kadang-kadang hidup kat sini. This is called interstitial. It's squeezed between regular sites of crystal sites. Regular crystal sites. So macam, so dia squeeze, dia duduk merempat lah basically. Dia tak ada tempat. Dia merempat mata rata, kesian dia. Tapi still it will bond, covalently bond with the silicon to give out extra, what they call it, extra free carriers, free electron. Okay, ni interstitial. Kalau substitutional, dia akan duduk kat sini. Dia akan ambil tempat silicon. Okay, tu maksud dia. So bila kita dope, when we dope, do you know how the process of doping? How do you do doping? Tak ada orang tanya saya soalan ni kan? Saya tanyalah awak. How do we do doping? How the process? Kita bancuh macam kopi ke? Macam mana? Since somebody Google, I give you 1 minute to Google. Dah? If you got the answer, let me know.
Oh, time's up.
Yeah, anybody? So how is the process of doping? How do we do it?
Okay, good.
Something like PN junction, madam.
Okay, teruskan.
Oh, jumpa gambar je, madam.
Okay, cuba awak share gambar apa awak jumpa.
Gambar video. Video, madam.
Okay, tunjuk video apa awak dah jumpa.
Oh, no.
Madam.
Can you forward? Forward. 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 Apa benda dia buat ni? Forward. Okay, saya tak tahu ni doping apa ni. Is it a semiconductor doping? Okay, it's not a normal doping that we talk about. Okay, scrap this one. The other people?
Photolithography.
Okay, you want to explain?
Basically, the process of it's like bombarding intrinsic semiconductor such as silicon with dopant ions such as phosphorus inside the chamber, basically, and depending on how strong the beam of the ions that you bombarded the silicon with, it will determine how deep the dopant will be embedded into the semiconductor.
So is it called
That's what I understand.
photolithography? Are you sure?
The process itself is not photolithography. What is it called? The process is called doping, but
Dah kenapa
inside
sebut
photolithography. Yeah, sorry about that.
Okay, awak jangan
But, yeah.
confusekan adik-adik ni. Adik awak ni.
Sorry about that. Sebab dalam ayat ni dia tulis apa benda yang apa, they put inside a same sentence, so I just say it.
Okay,
But
so
yeah, that's one.
can you understand from Faiz explanation just now? Aiman? Faham? Do you understand?
No.
No? Why not? Okay, tanya Faiz sampai awak faham.
Faiz, can you explain with the simple word? Explain using simple word.
Hang on, I'll try to do something here. Can I do this? Okay.
Awak nak buat apa?
Try to do screen sharing a bit.
Okay, quickly.
Where is it? Okay, here. Okay, so we have, oh shit. So we have a semiconductor here, silicon. And then we put it inside a chamber of some sort. And here we are filled, I believe, with the ion of a dopant such as phosphorus. Is it P plus? I don't know. The ion of the dopant. So this one in the case phosphorus, and then we beam the silicon with this ion. So bombarded with a phosphorus ion beam, and then depending on how strong this beam is, we can determine how deep the phosphorus will go inside the silicon. Something like that.
Okay, understand.
Okay?
Sorry?
Understand.
Okay.
Alright, thank you. So that's the process of doping whereby, stop sharing. So there's a process of doping whereby you are bombarding the ion into the into the layer of semiconductor. So if you put more of the ion in, the higher the concentration will be. So it's a gas. You make the phosphorus to become like a gas ion. Dia jadi gas tu, lepas tu you dengan lajunya you go and bombard, heat the semiconductor, and it will be inside the semiconductor. So when you do that, you don't know whether in the end it become interstitial or substitutional. So it can be duduk kat rata-rata ikut suka dia lah, macam tu. So macam tu lah. Tapi kalau dia jadi interstitial ni, dia macam akan menghasilkan macam defect. Sebab dia telah mengganggu lattice punya structure tu kan. Sebab tiba-tiba ada dekat celah-celah tu. So to add doping, okay, this is important. When you want to increase the free carriers we always like, free carriers because you give out a lot of current. With small voltage, you have lots of current, great. But there's also limit. In life, everything have a limit. Only Allah has no limit. So everything in life semua ada limit. So macam kalau kita engineer, we always talk about limitation of certain things. Because if kita design something, in the end there must be a limit. So the limit for the doping is, so if you keep on increasing the concentration of the doping to the semiconductor to make it more and more conductive, the problem is you are adding more of these impurities, which in the end will affect the lattice structure. Therefore, it will create defects. In the end, dia ada masalah lain. Bila banyak sangat. Kalau sikit-sikit dia boleh handle lagi. Bila banyak sangat, it will disrupt the whole thing. And you have defects. When you have defects, you have problem lain. So, saya rasa next, today we'll go through effect of temperature dengan defects lah. Ingatkan saya, 2 things. Okay, lagi? Soalan apa lagi yang awak tanya? Kita tengok.
Madam,
Yeah.
is there any parameter untuk stopkan adding impurities tu?
Stopkan apa?
How to know where it reach its limit?
Yeah, you have to do experiment. You have to do experiment to see in the end it has degraded the the electrical performance or no. So generally biasanya orang lain dah buat. There are other researchers who have done the experiment. You just go and check. For example, that's why we have research. So people will do that, they will publish. And then instead of us doing the same experiment, we just read their paper, say, oh, for silicon, pure silicon of this, the maximum before degradation, the phosphorus is this much. Okay. Okay, any more question?
If substitutional extrinsic happen, what happens to the original atoms at the original place? If it was replaced by a...
It was knocked out to go somewhere else.
Oh no, literally. Okay.
Dia akan knocked, literally. So it will go to be interstitial somewhere else. So dia defect pula juga. So
I'm sorry, what's the question again?
So my question?
Yeah.
So you know there's a substitutional doping, right? Where the original silicon atom is knocked out from its own place.
Right.
Okay, so where did it go?
Oh, okay.
Yeah.
okay.
But yeah, according to Madam, it went somewhere else. That might be, the atom might be interstitial inside its own material, so it might cause some other defect.
All right. Thank you. Thank you for the explanation.
Okay. Siapa Nash ni? Kenapa nama awak Nash?
Nash?
Answer me.
Nickname Madam.
Why your name is Nash?
Nickname Madam.
Nickname? Okay, write down your true name there. I don't know any Nash in my class.
Sorry, Madam. What is it?
Madam, in slide 19 about carrier concentration, why the x-axis of the graph using Okay. This is interesting question because the graph is also an important graph. So let's see. Okay, so slide nombor berapa? 19.
Yes. There is.
This graph, right? So Najwa was asking, do you know what Najwa means in Arabic?
Whisper.
Yeah, it's actually dalam Quran dia cerita jangan buat najwa. Najwa ni is like macam dia macam konspirasi. Dia kita buat so tapi orang Melayu ramai pakai najwa sebab kita cari maksud dia macam tu lah. Tapi the real meaning is najwa ni kalau macam kita ada organisasi, najwa ni macam dia buat kelompok kecil yang dia berbincang belakang untuk macam nak topplekan the organisation macam itulah. Sebenarnya tu yang dalam Quran maksud najwa. Tapi biasa kita orang Melayu faham najwa tu yang general lah, yang secret whisper. Okay, so this najwa, your question is kenapa dia macam ni right? Right or wrong? Tak dengar lah najwa.
Yes, madam. Dengar tak?
Tak berapa sangat. Awak jadi macam Azam lah pula.
Jangkit dah ada. Jangkit.
Sabar.
Wi-Fi kat sini tak okey sangat, madam.
Masa awak
Okey,
kat mana
dengar,
ni?
Kat Mahala.
Oh, awak dah sampai Mahala dah? Ke memang dari dulu Mahala?
Memang tak balik.
Oh, tak balik. Kenapa tak balik?
Okey lah, madam. Kalau COVID ni nak balik, sebab saya naik public. Saya naik bus. So macam nanti nak kena quarantine lah, apa dah. Macam tu lah.
Okay. Kenapa lah? Complain sikit. Awak pergi complain ke? Kan dia ada satu link yang boleh complain untuk internet tak okey tu kan? Awak tahu yang tu?
Tahu. Dia macam malam tadi dia macam tiba-tiba problem tu dia okey. Dia
tak kira
problem.
lah. Tak kira bila sekarang ni saya suruh complain. Okay. Kata supervisor saya, lecturer saya tak happy. Student saya tak boleh bercakap dalam kelas. Okay. So sebab you know why? Sebab dia orang kata student tak complain pun kita orang everything good. That's what they answer, ITD. So that's why kita ada pun kita kena complain je bersungguh-sungguh. So that kalau lagi ramai yang complain, hopefully they will do something faster. Okay. So apa ni Najwa, soalan awak apa? Cakap Melayu senang tak? Tapi tak, all of you need to speak English. We need to train you to speak English. Saya cakap Melayu tak apa. Sebab English saya dah okey. Najwa.
Kenapa yang exist dia ni yang sudi berbahagi dengan temperature?
Azam dengar tak? Kok lah Azam dengar. Dia
Kena naik volume lagi, madam.
kena naik volume lagi. Tu masalah. Dia pun tak dengar lah. Najwa, again.
Okay.
Shout.
Exist, dengar tak? Hello?
No.
Rasa macam problem microphone, not the Wi-Fi.
Apa Aina kat mana? Kat Mahala tak? Kat rumah. Saya rasa mungkin mikrofon lah saya rasa.
Sebab saya tadi okey je kelas.
There we go. Tu okey bang.
Okay.
Yalah. Okey, cepat. Sementara dia okey ni.
This yang dekat graph ni, okay. Why the is using the 1000 divided by temperature? Why we not directly using the temperature?
Okay, good question. Who can answer? Orang lain tak tanya soalan ni kan, maksudnya dia faham lah tu. So kita tanya orang lain. Aiman. Sini jawab Aiman, sebab awak tak tanya soalan ni. Maka awak kena jawab.
Sebab dia dah tanya, saya tak tanya.
Amboi, pandai pula jawab. Okay lah. Boleh, logik juga tu. So okay, saya jawab. Next time you can't run away. Okay, so Jawapannya ialah, this is one of important graph. So you need to understand this graph. So this is the intrinsic carrier density. What is it? What does it mean in intrinsic carrier density? What does it mean? Yang tu tak ada orang tanya. Aiman jawab.
The percentage of the
Asam
intrinsic.
jawab. Tak apa. Ha?
Percentage of the intrinsic.
Asam. You.
Percentage of intrinsic. Betul ke Aiman? Kenapa saya nampak rambut awak je? Apa masalah dengan kamera awak tu?
Sangat kot.
Boleh tak betulkan sikit biar nampak muka awak semua? Bawah sikit lagi boleh? Okey. Okey Aiman, saya jawab.
I think it is the concentration of carrier, intrinsic carrier.
Yeah, that's what the graph said.
So,
The density.
what is it actually?
The number of
Number of carrier.
the number of carrier.
What carrier? Electron or hole?
Electron.
Apa Najwa?
Electron.
So Najwa jawab electron. Orang lain?
The number of electron in conduction band or number of hole in valence band.
Okay. So intrinsic carriers, kita tak cerita pasal Fermi level lah itu kan, walaupun tak ada dalam ni. Awak patut tahulah semua benda yang saya suruh awak cari tu. This is the band gap, right? So, and then we have Fermi level. What is Fermi level? What is Fermi level?
It's in between, in the middle.
What is a Fermi level?
Energy level at absolute zero temperature.
No.
The probability to find free carriers.
Okay, good. So Fermi level is just a line to show the probability of having free carriers. Okay, so for a intrinsic semiconductor, the Fermi level is yang macam Azam kata is directly in the middle of the band gap. Why? Because it's the same probability of having free electron and free hole. The same. So whenever you, for intrinsic semiconductor, right? If you have the one that we be drawing before this, semua yang saya duk draw sebelum ni. Saya duk draw ni semua ni. This is actually, you never ask me whether this is intrinsic or extrinsic. So everything that I was drawing, talking about recombination semua ni, we are talking about intrinsic semiconductor, which means that for every electron for every electron that been generated here, one hole will go. So when we talk intrinsic, it's always about pairs. It's the same that happens to electron, it will happen to the hole. Okay, kalau the extrinsic lain sikit. So going back here. So the Fermi level for intrinsic is in the middle because it's the same probability of finding free electron and free hole. So duduk tengah-tengah. Okay, so so it means that the number of as we know for intrinsic semiconductor in your degree first year, the number of electron equals to number of holes. Kan? Kalau intrinsic ni. Intrinsic sama electron hole tu is the same. Kalau ada 5 free carriers of electron, it will be 5 of free carriers of hole. So intrinsic carrier density, it means that both the electron hole number of free carriers per unit area. Sebab di density per unit area. Okay, so that's what intrinsic carrier concentration means. So this is like for pure semiconductor. Now, so for pure semiconductor, in order to get the free carriers, you can how do you get free carriers in intrinsic semiconductor? How do you get free carriers in intrinsic semiconductor?
Provide it with energy.
Generation.
So through generation, right? Through generation.
Yes, generation.
So through generation, when you to the generation process or generation mechanism, and what when for the generation, it needs to have energy, and the energy can come from the heat or the light or whatever other sources. Okay, so now that's how you generate free carriers in intrinsic semiconductor. Okay, lepas ni ingatkan saya cerita pasal Fermi level for extrinsic. Takut saya terlepas. Tiba saya terlepas, nanti keluar juga dalam final. Habis lawak. Okay, then so this see, this is a graph of the intrinsic carrier density versus temperature. Tapi ni kenapa 1/T? So biasanya student, kadang saya tak explain ni, saya duk harap student engineering patut faham lah. Saja je saya tak explain, tapi sebab awak tanya, saya terpaksa lah explain. So you can see here, you have bottom and top. So this is how to read this graph. And you have to see this is actually a log. The y-axis is actually a log plot. Dia punya line tu tak sama. Kalau dalam semiconductor ni banyak kita pakai log plot. Okay, bukan linear. This is log, this is linear. So we plot log linear graph. And the two common. So so you can see here, you can plot this. So sini sebenarnya, why do you plot like this? Because in order to get the straight line, because the intrinsic carrier density is inversely proportional to the temperature. Kalau kita plot against temperature ni, dia akan dia tak akan dapat straight line. Okay, that's why. Sebabnya kalau nak faham, kalau yang ni susah nak baca, normally you baca kat sini. Yang ni make sense, more sense to us. For example, so you can see as you decrease the temperature, what happens to the
Density.
Density?
Decrease.
As you decrease the temperature, what happens to the density? Increase or decrease?
Decrease.
Increase ke decrease?
Increase.
Increase.
Ada yang jawab increase, ada jawab decrease. Awak ni, ya Allah, sikit tengok ni ya. So ni kan, ni as we decrease the temperature, right? So as we decrease the temperature, what happens? So tengoklah kat sini, patutnya awak tengok kat sini, temperature ni 1.
Yes.
So ni temperature 20 degrees. Ni kalau temperature 200, this the value. So this is like 10 kuasa 12, ni 10 kuasa 17. So as you decrease the temperature, the carrier density decreases. Okay, that's how you read this graph. So you need to able to read. Nanti saya kata, okay, can you find out, I will change the temperature from 340 to ni. Can you estimate what's the number? So walaupun saya tak ajar dalam kelas ni, tapi I expect you 4th year should know how to read graph. Okay. So you can see in this graph, there are 3 material. Dia plot 3 material. So dia plot gallium arsenide, silicon dengan germanium. So you should also look at this graph and try to understand the relation between the 3. So if I ask you, what is the best material to use at 100 degrees C to make a diode? What is your answer?
Gallium arsenide.
Gallium arsenide, why?
Because it got many free carriers.
Because at 100 degrees C, it gives out the highest number of free carriers. So it's good. So and you can see it's this number of carrier density is exponentially increases with increasing temperature. So as you increase the temperature here is 1000 degrees. So this is a straight line, and this is not linear. This is log linear, meaning that the carrier density increase exponentially with temperature. So as you keep on increasing, so maknanya yang ni, which means that now I want to talk about the effect of temperature. Okay, let's talk about effect of temperature.
The higher the temperature, the higher the density of free carriers, right? Wait a minute.
Okay, so if I because we know the free carrier depends on the energy. If you put more energy if you give more energy to the electron, there'll be more probability of the electron to be excited. So let's say this is let's say let's say this is 18 degrees C, this is 25 degrees C. So for the 25 degrees C, you have more free electron that are having enough energy to be excited to the conduction band. Okay, and vice versa, the same. So as you increase the temperature, you will have more free carriers. But the problem with the normally, if you design if you look at your, I don't know if you remember your electronic ke apa dulu, masa electronics dulu, we have to calculate the gain, right? If you remember, gain. Remember, you have to calculate the gain in the BJT, the gain, the MOSFET gain. This gain, when you design the circuit, in the end to have a specific gain. Okay, so we as an engineer, we calculate the resistor. Remember, you do all this calculation, calculate resistor apa semua tu, in the end to get a certain gain. Now, the problem is with semiconductor, it's very sensitive with temperature. So that's why if you buy something of a semiconductor device or equipment, they will have a range of temperature. To use. So because it's sensitive to, we can reduce the sensitivity to temperature by engineers they will play with the circuit. In the end, the circuit able to counter this temperature dependence. But generally, if just no circuit, just the device itself, the semiconductor, is very susceptible to changes of temperature. Okay, so that's why if you use semiconductor or IC in Malaysia, and you go to the desert over there might be slight changes of the performance of the device. Or you go to the winter, also we have some changes a bit. There will be like a range. So it means that semiconductors are very sensitive to temperature. So we need to be wary of that. And the problem with if you say, okay, madam, so there are two ways to increase how many ways to increase the free carriers in a semiconductor? One way is through this generation. So to increase, what are the ways to increase free carriers in semiconductor?
Doping.
Doping, yes, good. So doping, and number two, temperature. Right? But doping you can control. We engineers, we love anything that we can control. So doping you can control how much. But temperature, it's actually something that you cannot dia slight change but dia exponentially change lah. Kalau you tukar sikit je dia akan naik. So you don't know, and then the temperature will also not be stable. Kadang-kadang dia naik sikit, turun sikit, you know. Even 0.1 degrees pun will affect the performance of the semiconductor. So normally the effect of temperature we don't like. Okay, in semiconductor, when design, we don't like the effect of temperature because we cannot control. And bila kita design dah nampak, sebab the temperature will change the number of free carriers, calculation kita semua lari. So that's why we try as much as possible to avoid this effect of temperature lah in our apa nama design. Okay. Any question? Okay, saya dah cerita effect of temperature. Okay, apa lagi nak cerita?
Extrinsic, madam.
Extrinsic. So extrinsic. So this the so if this the extrinsic semiconductor, silicon and type. Where's the Fermi level?
Closer to conduction
Closer
band.
to conduction band.
Close to the conduction band. Why?
You have more probability to find free electrons.
So it shows that it's okay. When you have the Fermi level close to the conduction band, what it means actually, bila kita dope, okay, yang ni saya dah cerita lagi. So remember we start with intrinsic first. Okay, saya kita undur balik. Let's say this is the intrinsic silicon. Okay, the Fermi level is in the middle, right? Then we dope this. Okay, when we dope, remember that we say pure semiconductor, there shouldn't be any energy level inside the band gap. Remember? Right? That's why it's called forbidden band gap. There shouldn't be any energy state or level inside the band gap. But when you dope it, you're adding impurities. It's no longer ideal. It's no longer pure. So what happens is when you put a dopant to the semiconductor, it will introduce energy level inside the semiconductor band gap. Okay, so for example, now it become like this. Suddenly kalau this is, you dope it with n-type, you dope it with donor atom to make it n-type. So what happens is by doping it, you are introducing, because it's impurities, you introducing a energy level over here. ED donor energy level. Okay, which now it means that at 0 Kelvin, at 0 Kelvin, do you have anything moving in 0 Kelvin?
No.
No.
In true experiment in life, this our human life ni, nobody can do any experiment at 0 Kelvin. Never, because everything freeze. All atom freeze. The electron orbiting the electron will stop moving. So it means that nothing will work at 0 Kelvin. So the lowest maybe 0.001 Kelvin. So they do very expensive. It's very expensive equipment to go very low. Normally what is the temperature for room temperature in Kelvin?
293 to 83 something.
Roughly we say 300 Kelvin. Right, in Malaysia maybe 300 Kelvin. Kalau yang 295, 298 ke apa, 2 times 2 tu dia dekat UK, US, dia sejuk. Kita kat Malaysia ni 30 lebih temperature kita, betul tak? Kita tak 20 lebih. Kalau dekat kat tempat dia 20 lebih, tempat kita 30 lebih. So let's say easy, you say 300 Kelvin. So the 300 Kelvin is our room temperature. If you want to reduce the temperature, easy, we use liquid nitrogen. Ini saja je saya cerita. You know what is the boiling point of liquid nitrogen?
Good question.
No. Madam.
It's 77 Kelvin. Okay, have you played with liquid nitrogen before?
I wish.
You wish? We can
Yeah.
play, we can buy. So when I did my PhD, every day I'm playing with liquid nitrogen. Is you have to wear a very thick glove. If the liquid nitrogen falls on you, you will get like macam frostbite tu, tangan ni boleh jatuh macam tu je. So it will freeze everything and dia akan tercabut macam tu. It's how dangerous that it can be because it's very cold. So in my PhD, what I did was kita orang kena cool the detector. Semiconductor detector, we need to cool it to very low temperature in order to reduce the noise. Nanti awak akan buat benda ni lah, assignment nanti some of you will do on detector. So liquid nitrogen at 77K is very cold already, but it's not, so that zero, to go lower it become more and more difficult. Liquid nitrogen is still affordable lah, kita boleh buat lagi measurement tu kat Malaysia pun. Okay, so now at 0 Kelvin nothing moves. So at 0 Kelvin, all ni I'm drawing at 0 Kelvin, all the electrons are here. Oh bukan, dia kena duduk atas. Sorry, mana tadi? Okay, ni 0 Kelvin. 0 Kelvin, there's no energy, right? So do you have free carriers at 0 Kelvin?
No.
No.
No. Even for extrinsic. Intrinsic memanglah tak ada even 77 pun belum tentu ada free carriers. But sebab it has to go to, it need a lot of energy to go from here to here for intrinsic. But for extrinsic, at 0 Kelvin, electron, because of the impurity that we put, the electron are there in this energy state, energy level. So if we increase slightly, so if you say increase slightly the temperature, say room temperature, just room temperature. Room temperature, intrinsic, we have a few, not many. So that's why intrinsic carrier concentration is very low compared to the extrinsic, so the n-type, right? So at room temperature, what happens is this electron here will we assume all will be excited to go to the conduction band. Okay, so which means that in the energy level of the donor leave with nothing, no electron anymore. All has been excited to the conduction band. Okay, so ni at room temperature. So in that case, the Fermi level of the Fermi level is always between two energy level. Kalau Fermi level between of intrinsic between conduction band and is between conduction band and valence band. For extrinsic, it's between the conduction band and the donor energy level. So Fermi level will be in the middle of the two energy levels. So the Fermi level of n-type will be here. That's why dia punya explanation why you have the Fermi level over there. So normally we don't draw, if later for the PN junction, we don't draw the energy level of the donor. We just draw the Fermi level. If you draw the Fermi level, we already know that the Fermi level in between the energy level of the donor or acceptor atom. In this case, donor atom. Okay. So if I don't tell you in the exam, I just give you this picture, you already know that this is n-type. I don't have to tell you anything. Look at this picture, you know the Fermi level there is already n-type. So for p-type, how does p-type macam mana? P-type you do with what?
Aluminium.
Boron. So you do with boron, which means that p-type you have extra hole. Okay, you have the majority carriers are the hole. So the same thing happens, right? The same thing happens. You have the energy level of the donor. So the Fermi level is in the middle.
Oh, it's still got energy level of donor.
Silap. Bukan donor, dia panggil acceptor. Sorry, thank you.
Yeah.
So energy level of the acceptor. Thank you. So then you have the Fermi level and the hole are here. So at room temperature, all the hole will be excited to go to the valence band. So you are left with, so all, we assume all. So that's why in the end, we just draw the Fermi level of the donor atom, acceptor atom. Okay, so macam tu. So that's why, and this is fundamental. Jangan tertukar yang mana Fermi level atas bawah tu, sebab lepas ni kita akan guna ni banyak kali. Make sure tak confuse. Any question on the Fermi level? No? Okay, any more question? Tak ada dah. What is direct semiconductor? Oh, maksud awak, Aiman.
Is it because the semiconductor has direct band gap? That's why it called direct semiconductor?
Yes. Kat mana awak baca direct semiconductor ni?
Slide.
Slide nombor berapa?
Oh, 14.
14. Kat mana?
The most interesting. The
Okay.
6 compounds are all direct semiconductors.
Oh, all the direct semiconductors and span, yes, direct band gap. When I say direct semiconductor, it means direct band gap semiconductor. Okay, any more question? Soalan Aina ni saya tak faham. What is trap level? Is it some kind of energy? Okay. It's a good question. Okay, now let's go to the defect. I want to talk about defects. Defect is important, especially to you, Faiz. Okay. Defect. Now, we talk about defect that will affect, kita pernah cerita defect kan? Pernah cerita? Pernah cerita tak? Apa yang kita cerita pasal defect?
Vacancy.
Vacancy.
That's one type.
Dislocation.
Okay. So I give some introduction on the defects here, whereby the defect can be, can be from vacancy dislocation, and the effect of the defect, you can see the defect to be physically active, it's physical, you can see it, or it can be electrically active, it affects the electrical properties, and it can be optically active, it affects the optical properties. So how does actually it affecting the how do we show it in energy band diagram? Okay, so we for physical, as mentioned, we look in the microscope, we can see line missing of certain colors, it shows the physical. For electrical and optical, normally in order to explain this, we put the defects inside the energy band diagram. So channel sini. Okay. Okay, so this it doesn't matter whether intrinsic or extrinsic, so it can be so let's assume it's intrinsic for now. dia sama je kalau defect tu dekat mana-mana pun, intrinsic ke extrinsic, dia punya effect tu sama. So so this let's say this is silicon 1.1 EV, the band gap. So then we introduce defects inside the structure. So again, as we say, pure semiconductor ideal, there shouldn't be any energy state or energy level. Kalau state dia apa beza energy state dengan energy level? Kalau state dia macam ni, kalau level dia macam ni, dia panjang, maknanya dia banyak of multiple of the energy state become energy level lah. So okay, so apa soalan dia tadi? Apa saya tanya tadi? Kalau kita introduce defect dalam semiconductor pure, normally pure ideal, you don't have any energy level inside the band gap. But we understand just now when we add impurities, when it's no longer you add other things, it disrupt the ideal of the band gap. So another thing that can introduce energy state or energy level inside the band gap is defects. So for example, you look in the microscope, you see like lubang ke, you see a line there. So how does that translated into the energy band diagram? It will translate in terms of energy state. So dia boleh jadi macam ni. And we call it sometimes we call it ET, trap. Defect and trap the same thing. Kalau baca kadang soalan tu trap, kadang defect ke, it's the same thing lah. Because the defect will be a trap. Dia macam trap ni, it will trap carriers. So okay, so energy, this defect can be anywhere inside the band gap. So dia boleh duduk kat situ, dia boleh duduk kat sini, dia boleh kat sini, ikut suka dia. Okay, ikut suka dia. So it depends on the type of defects. That's why there are people do research and they will find out from the experiment where are the trap level. Yang ni yang dia orang pakai di LTS dengan Faiz. Di LTS yang kata kita tak ada equipment tu, they can know the trap level kat mana dalam band gap. But in our university we don't have that equipment. Okay. So they can do that, they will know the trap level lah. ET ni dekat, macam mana dia tahu trap level? Macam ni 1.1 EV. So in the middle it will be 0.55 EV macam tu. Hak ni maybe 0.1 EV. Hak ni 0. Kan? Okay, 1.0 EV ke? That's how they give we know the defect based on the EV, the energy level of the trap. Okay. So the trap can be from this everywhere inside. It depends on the trap. Okay. So how does the trap behave? Let's start with the one in the middle here. Okay, trap ni. So remember we talked about generation before. Generation is what?
Free electron.
Excited
Generate free
to the
electron.
conduction band.
Again. Repeat. What is generation?
Electron excite from valence band to conduction band.
Generation is a process where free carriers are being generated when electrons are being excited from valence band to conduction band, and holes being excited from conduction band to valence band. Okay. So walaupun saya cerita tak pernah dengar ayat yang penuh dalam exam, awak jangan jawab macam tu lah. You need to jawab yang dengan ayat yang semua orang boleh faham. Okay, profesor dekat UK, US pun boleh faham awak punya jawapan tu. Okay, now, so kalau nak tahu ayat paling best, baca buku lah. If you keluar ayat buku tu memang power lah. Okay, now that's generation, right? So we say there is generation through so generation dia memang kena pergi daripada for electron, for valence band to conduction band. Now, So normally generation will go through macam ni kan. Betul tak? That's normal that I talked to you before. But whenever you have defects, okay, let's say you are, so if you are the electron, okay, so you are standing in the dekat valence band ni, and you want to go to conduction band. And then tiba-tiba awak nampak ada energy level kat tengah ni. Yang mana awak akan pergi? Route tu ke atau route ni? A ke B? Kalau awak elektron.
B.
Hmm?
B.
Azam jawab B, orang lain? Hambali?
B.
Tak dengar suara awak. Hambali?
B.
Why B?
Because it got a defect, so it got trapped. Because of the defect, it got trapped.
So why? Why do you want to go? Why do you want to be trapped?
I don't know.
You cannot answer. You don't know. So think again. Why? If you are electron, you want to go direct, or you want to go through the defects? Why? This is logic. Thing.
Shorter path.
What do you mean by shorter path? This is the y-axis is energy.
Oh.
It depends on how excited the electron is, right? Like if you get enough energy, can I just jump to the conduction band?
Go to track.
If you are the electron, which one do you choose?
But probably A.
Pak Izzah jawab A pula. Orang lain?
B, Madam B.
Azam B. Hambali?
A,
Madam.
Aina?
A, because after all it is exciting to go to the connection band kan.
Najwa? B? Tak dengar lah. A ke B?
B.
Aiman?
B.
Huh?
B.
Why B, Aiman?
I think because the electron think that the region where there is the defect, the trap, it thought that it is where the conduction band is.
So you're thinking macam electron tu tertipu ke? Tak faham.
Dia
Electron.
Sentient.
Less energy, Madam.
dia ingat kat situ, so dia perlukan energi yang sikit je lah. Tengok tak kena lagi lebih. Gitu.
Logik.
Okay, dah dekat dah tapi macam tertipu, cuma terkelakar sikit lah. So alright, so I always tell the student, you need to imagine you are an electron. Tapi kalau kita imagine lagi senang nak faham, you know. So imagine you have a river, near river lah. And then you want to jump from this side to the other side. Okay, the same thing. So you want to jump, you need to have energy, right, to jump. Betul tak? Kan you kena lari laju, lagi jauh you boleh pergi, right? It means that more energy you put the kinetic energy to go to pass it. So sama juga dengan elektron ni. So sekarang ni kalau dia kena jump kat sini, katalah ni katalah nak mudah hidup kita buat ni dia punya apa ni, band gap ni 1.0. Okay, so here this A, in case A, this electron has to gain energy of 1 eV. But kalau through this, the trap, the electron has to gain only 0.5 eV and then another 0.5 eV. The probability of gaining 0.5 eV twice is higher than just what mana kita nak. Kalau kita melompat pun, for example di sungai ni, tiba-tiba ada nampak macam ada titi ataupun ada tempat yang boleh melompat. So kalau kita pun manusia, kita akan choose to we will choose to lompat kat sini, berhenti sekejap tu lompat lagi, right? The energy will be less. Untuk dapat satu energy gis ni lagi senang yang ni daripada pergi dapatkan 1 EV terus. So jawapan dia ialah B. So the trap is assisting the generation. Okay, and this is nama dia, sebab tu ni normal generation yang ni. Kalau ni kita panggil dia trap assisted generation. Nama dia. So maknanya the trap or the defect is assisting the generation. It means that if you have defects, you have more free carriers or not?
More.
When you have defects, you have more free carriers or not? More or not? Answer me.
Yes, more.
Faiz jawab yes, yang lain?
Yes.
Azam?
I think no,
Soleh
madam.
jawab yes.
I think no.
Azam jawab no. Kenapa no, Azam?
Excuse me.
Because the ET maybe has some limitation.
Okay. Let's say, okay, apa soalan saya tadi? Kalau kita ada trap ni lagi, apa limit dia? Apa yang limit dia? Dia ada satu kat sini. Kalau saya ada, for example, saya ada satu yang ni. Case saya maknanya, this case A dan case B ni, yang mana yang akan lagi dapat banyak free carriers? Okay, mungkin satu tak nampak lah. Awak tak nampak satu. Okay, let's next. So kata kita ada 3 trap. Sebab defects ni dia bukan satu je kan. Dia ada, when you talk about defects, you will say defect density. Number of defect per unit area. Okay, or per unit volume. So which one you will get more free carriers? With defect or without defect?
With defect.
With defect.
Defect.
Of course lah.
Good. Hello?
Defect tu assisting. Dia memudahkan. So material, semiconductor material or semiconductor devices with defects will have more free carriers. Is it good or bad?
Good.
Bagus ke tak bagus sebenarnya? Answer me.
Good.
Good. So we should have a lot of defects. We should introduce a lot of defects in our structure.
No.
Not many, but
So jom kita rosakkan semiconductor semua. Yang bagus ni kan.
No, we don't have any defect because we cannot control how many defects. Like we can reduce it.
The problem is we cannot control the defects. And we don't know defects ni juga dia macam random. Kadang-kadang dia boleh duduk kat sini, kadang-kadang dia boleh duduk kat sini juga. Okay. Right. So defects we don't like. Number one, because we cannot control. It's unpredictable. And then we don't know, every time we had a defect, we don't control the amount of defects. So when we design any semiconductor device, we cannot predict. So that's why for prediction, in order for us to design properly, we prefer there's no defect at all, so that we can know how many carriers, how much current will come out, how much amplifier you need, right? So defect is actually, and also defects ni dia akan increase the free carriers more than what we want, more than what we design. Therefore, in the end, we have heating problem, and which will rise to heating problem. Heating is actually, nanti kita ada satu in BJT. Heating is actually a problem sebab bila kita heat, dia jadi heated, dia akan vicious cycle. Dia akan jadi bagi banyak generation. Kita heat dia banyak lagi. Macam in the end, benda tu akan meltdown. Sebab dia macam reinforcing. Dah lah panas. Panas pula akan membuatkan elektron lain tu naik lagi. In the end, kita tak boleh control.
Generation.
Okay. So that's the answer. So now, okay, sekarang ni kita cerita pasal trap yang tengah-tengah ni kan. Apa jadi kalau trap tu bukan tengah? Macam ni. Kat sini. Do you still have trap assisted generation or no?
Yes.
Yes.
Because if let's say that point is 0.8 and the rest is 0.2, still there is the 2 steps before straight away like just now.
Okay, so there will still be trap assisted generation even if the trap is not in the middle. Okay, if in this case, case A and case B here, where this is the trap is in the middle, this one at 0.5 EV, this is at 0.5 EV, and this one is at say 0.8 EV. Which one will give you more free carriers? The probability at room temperature, A or B?
B.
Why B?
The probability. Sorry, Ashram.
Why B? Why B? Satu lagi sebagai contoh lah, let saya confusekan awak lagi. Satu lagi saya letak kat
energy,
sini.
madam.
Ni. Okay. Saya buat satu lagi C. Kita KC. So antara A, B and C. Yang mana yang give you more free more free carriers? A, B or C? So this is the trap energy here is 0.1, 0.2 lah kata.
It's the same as that.
Apa jawapan antum? Anda semua. Cakap bahasa Arab saya. Azam. A, B or C yang paling banyak free carriers?
I say B.
B,
If
madam.
is B, Azam?
B.
B,
Swan.
Hambali?
C.
Solihin?
C.
Okay, so yang jawab C. Najwa?
Madam, can C jump to A?
Apa? Can C apa?
Can the electron from C and jump to A and then go to covalent bond?
Possible, tapi kita assume dia individual cases now. Possible. Boleh juga macam tu, tapi dia panggil tu memang dari dia panggil apa ni hopping mechanism. Yang tu kalau buat PhD kita cerita pasal tu lah. Kita tadika ni tak payah lagi belajar tu. Dia ada banyak mechanism yang complicated. So dia in order to explain. Tapi untuk level kita ni kita assume dia separated lah ni. So apa Najwa? A, B or C?
B.
Najwa pun jawab B. Aina?
C. I change, madam. I change to C lah.
C. Aina, mana Aina?
I dah confused.
Allah, tak payahlah confuse. Confuse apa? Confuse apa?
I am trying to do maths here.
You're going to do mathematics. Wow, hebatnya. Cerita sikit matematik macam mana awak buat?
Is that the 1/8 divided by times by 1/2/8, something like that? The probability
The
question.
probability Okay, brothers and sisters ni tak payah pakai matematik, dia pakai logik akal dia. Dalam semiconductor ni sebenarnya tak susah as long as kita boleh berfikir pakai logik kita. Logik yang disertakan dengan ilmu sedikit lah. So biasanya soalan-soalan saya pun dalam final exam dia akan banyak logik. So dia tak ada jawapan direct tau, kena fikir. And dia mungkin ada beberapa jawapan. Dia tu nama dia open ended. Dia bergantung pun macam mana you fikir. So sekarang ni jawapannya ialah jawapannya ialah B. Why? Sebab biasa ni soalan yang common saya tanya dalam final exam. Ada sudah jawab salah. Seperti biasa kan. Tapi kat awak, you are lucky I'm covering this here. Mungkin saya tak pun dalam final mungkin. So kalau saya bubur pun dalam soalan style lain. So ni exactly soalan yang saya tanya dalam final normal final saya. So the answer is B because remember kalau you need to remember you are the electron. Kan saya selalu kata awak kena imagine awak electron tu awak cuba jump sungai ni. So kalau awak cuba jump sungai ni yang ni awak kena jump, awak kena ambil lajak. Senang ke nak point 8 ni, lepas tu yang ni senang. Nak dapat yang point 8 ni payah tak? So yang ni out jump senang, tapi lepas tu kena jump 0.8 pula. Right? Pun susah. So yang ni 0.5 awak jump, ambil nafas kejap tu jump sekali lagi. So the easiest route, the trap in the middle is always the most active. The trap or defects in the middle of the band gap is always the most active. So lari sikit dari situ, maknanya kalau nak memang paling dahsyat punya defect, it has to be in the middle because that is the most active and they akan create more free carriers. Okay, so this is when we talk about electrically, when we say the defect is electrically active, like macam ni. So you can have generation through the defects. Can you have recombination through the defects as well?
You lose energy, right?
Boleh tak?
No. So,
Okay, recombination is important for LED and lasers. Why? Because in order for you to get light, remember we told before, you need to recombine, right? And the energy loss is the light coming out. Remember? We talk about this, right? So recombination is very important for LED and laser. It doesn't mean that for photodetector, recombination doesn't occur, but it's not affecting the performance of the device. So maknanya it's still occurring, tapi we don't care sebab it doesn't affect what is important for the device. So recombination the defect will affect the recombination and it will affect mostly, that's why we call it optically active. Why so? So normally in recombination, it will recombine like this, right? From band to band. And this, nama yang ni, nama generation yang macam ini, generation yang direct ni, nama dia band to band, yang ni band to band generation. Band to band generation. Yang ni band to band generation. Yang ni trap assisted generation. Okay, right? So yang ni kita panggil band to band recombination because it's from valence band, connection band to valence band, band to band. But you can have if you can also have recombination through defects. And ni nama dia kita panggil recombination through defects. Okay, so the electron can recombine through defects. So whenever, remember, if this is a direct bandgap material, say this is gallium arsenide, is 1.4 eV. So if you have a band-to-band recombination, it will give out light photon of the energy 1.4 eV. Okay, it will give light of the energy 1.4 eV if it is a direct bandgap material. Let's say this is gallium arsenide. But now this gallium arsenide have a defect. Okay, so now this gallium arsenide have a defect. So also when the electron want to jump here, it's easier to jump here and then here instead of direct to the band to band. If you want to jump pun, awak akan, walaupun turun bukit pun awak suka juga, you don't have to jump much. So the electron the same. So whenever there's a defect, the electron will recombine through will have this recombination through the defects. And what happens when direct bandgap material have a defect and the recombination happens through the defects, so maknanya here the energy, so let's say katalah trap energy at 0.2 eV ya. So how much is the energy loss over here?
1.4. No, 1.2, sorry.
1.2 eV, right? Because 1.4 minus 0.2 it becomes 1.2 eV, and this this
Does not generate
energy
light.
loss, it becomes photon or phonon? This 1.2 eV, is it a photon or phonon? It becomes a phonon. It's no longer become light. Because remember yang EK diagram kita draw sebelum ni? Kan? Yang kita draw baru ni, EK diagram tu kan? Yang tu macam ni. Indirect bandgap material. When they recombine, it has to go macam ni. It will change the momentum for indirect bandgap. So the same here. When you have when you have defects in a direct bandgap material, what happens is when they recombine through defects, they changes momentum. Therefore, you lose the photon. It becomes phonon. It becomes heat. So that's why if you have a lot of defects in a laser or LED, you have less light coming out. So you will still have light coming recombine through band to band here, but you also have light coming here through here. So if you have more defects, less light, and they akan tak efficient lah. You put voltage banyak ni, sikit je light coming out. Okay, that's why a good LED light yang awak beli untuk rumah awak tu kan, the more expensive one, for the same amount of voltage that you put, you have more light coming out. That's efficient LED. The one that non-efficient, maybe you have a lot of defects, then you lose the free carriers through non-radiative recombination. So nama dia pula, another name for this. So when you have recombination through defect ni, we call it also non-radiative recombination. Because the recombination doesn't give out light. And the band-to-band recombination for direct bandgap material is called radiative recombination. Radiative recombination means just that radiation that gives out photon. Okay, I think that's covered for the defects. So again, the defects also affected by temperature. These defects is also affected by temperature. I will not teach you. You need to think on your own. And apa nama ni, I may ask in the exam. Okay, because you understand the concept of temperature. So kalau yang ni pun patut you boleh apply that concept with this defect. Okay, any other question before we end the class? No? Aina ada soalan lagi? Okay, tak ada. So next week we'll go through we'll go through a bit more of the material physics, which is we talk about mobility, conductivity, drift and diffusion current, and then
Tu pun ada kat dalam paper.
apa?
Drift and diffusion, electron drift.
Yes, so we'll go through that. Then in the end baru kita akan masuk PN junction is the first device that we'll go through. Ni baru tadika lagi, tak masuk darjah 1. The basic kita covering the fundamentals before we go to the device. PN junction. PN junction you can see here, that one ni. Dia punya ni tak cantik. This dia punya apa nama ni? Energy band diagram. Tapi drawing dia tu tak berapa clear.
You go to diffusion.
So I will give you, bila sampai sini I will give you a video that I made on the how do you draw the energy band diagram of a PN junction. Kau boleh tengok berjuta kali. Okay. Tak ada soalan lah? Okay, kalau tak ada soalan kita tutup. Can we have a brother to recite the doa please?
Let me start. Bismillahirrahmanirrahim. Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Bismillah. Allahumma inni na'udzubika min hammi wal hazan wa na'udzubika min ajzi wa salam wa na'udzubika min jubni wal bukhl wa na'udzubika min ghalabati ad-dini wa qahri rijal. Sallallahu ala Muhammad wa ala alihi wasallam. Alhamdulillah. Amin.
Alhamdulillah. Thank you very much. See you next class, insyaAllah. Assalamualaikum warahmatullahi wabarakatuh. Faiz, you join the meeting at 1 dengan FIP tu.
Wait, what?
Ada meet out dalam FIP saya punya tu tak?
WhatsApp group ke?